Welcome. In this session on natural deduction, we'll explore the basic semantics of propositional logic. Semantics is a word that is the meaning of something, and propositional semantics is the meaning of formulas in propositional logic. In our case, the meaning is a truth value, and there are only true truth values that we have, and these are either T for true or F for false. That is, when we're working with propositional logic, a statement is either true or false and nothing else. A model is, so those are truth values. A model is assigning or assignment of a truth value to every atom in a formula. And this is also called evaluation. So some authors will refer to this as a valuation. And the reason that it's called evaluation is that it's an assignment of a value. This now allows us to explore the basic semantics of the operators that we've been using in previous sessions. Suppose that, let's suppose, so we will let phi be a well-formed formula and psi be a well-formed formula. The first operator that we considered was negation. In this case, negation has only one operand, which is a formula. And what we do is we write the formula, and then we write negation of the formula. And the way that we express the semantics of this operator are as a truth table. A truth table is all possible assignments to that formula. Eventually, a formula is either T or F because those are the only assignments that are possible. I'll write them in the order T, then F. And the semantics of negation correspond to what we think of as the word not. That is, if a formula is true, the negation of that formula is false. If a formula is false, the negation of that formula is true. The next one is conjunction. Conjunction has it's an operator that has two operands, the left conjunct and the right conjunct. So we have phi and psi, and between them, phi can take on two values, psi can take on two values. So in total, they can take on four values. I'll write these as both are true, or the left is true and the right is false, or the left is false and the right is true, or the left is false and the right is false. And now we can define the semantics or the meaning of conjunction. And this is phi conjoined with psi. If we think of this operator in terms of the English word and, a compound sentence of two formulas is true, requires that both of these be true, and that will be false if either one of them is false. Going through this row by row, the left conjunct is true, the right conjunct is true, the conjunction is true. I'll write these under the operator. Here, the left is true, the right is false, so it's not the case that they're both true, so that is false. Here, the left is false, the right is true, so that evaluates to false. And here, the left is false, the right is false, that evaluates to false. And we can see that this truth table is capturing what in English we mean by the word and. Our next one is disjunction, and disjunction is an operator that has two operands. So again, we have phi and psi, and between them, they can take on four values. So this will be true, true, false, false. This will be true, false, true, false. And we can now, by means of a truth table, define the semantics of disjunction. So phi disjoined with psi. In English, this is the inclusive form of the word or. And this will be true if either the left or the right disjunct is true. Here the left disjunct is true, so it's true. Here the left disjunct is true, so it's true. Here the right disjunct is true, so it's true. And here the neither disjunct is true, and so this is false. The other operator that we have in propositional logic with natural deduction is material implication. Here we have an antecedent formula and a consequent formula. These can take on the four truth values that we've written in the other tables. And so we can now just use our routine pattern to fill these in. And now we're interested in defining the semantics of material implication. And so this is phi materially implies psi. And we can fill this in a number of ways. One way we can do it is by recalling one of the sequence that we proved, which is if a formula is true, then that formula is material implied by any other formula. So we can go along the rows where the consequent is true and simply fill these in. Here the consequent is true, and so it is material implied by anything. Here the consequent is true, so it's material implied by anything. Another rule from natural deduction that we can prove is that a false formula implies anything. So wherever we see the antecedent being false, we can fill that in as being as a material implication. So here, a false antecedent implies anything, and so that must be true. The remaining case is, we can reason this out using modus tollens. Is modus tollens, if the consequent is false and the material implication is true, then we could show that the antecedent must be false. Here we have false and true, and that means that the material implication cannot hold, and so we have the truth table for material implication. We can use truth tables to explore the semantics of more complex formulas. Suppose that we're given the formula P implies Q, or Q implies P. We can convert this to a well-formed formula with the addition of some parentheses. Our question now is, under what models is this disjunction true? In order to find that out, what we can do is we can write down a truth table. Here the truth table contains two atoms, P and Q, and P and Q can have four truth values between them, which we can write in our routine way. Now, in order to handle this more complex formula, let's take each of these disjuncts and write down its rows of its truth table. So the first is P implies Q, and that we already know is true, false, true, true. The right disjunct is Q implies P, and here we have to take care. True implies true, that is true. False implies true, that is true. True implies false, that is false. False implies false, that is true. And we can now form the disjunction of these implications. And this disjunction is true if either the left or the right disjunct is true. So this will be true. Here we have the right one is true. Here we have the left one is true. Here we have both are true. And this truth table is telling us that no matter what model we pick for P and Q, this disjunction of implications always evaluates to true.